Okay, now we're moving into the non-base E exponential forms. So we have a to the x, where a is not necessarily equal to e. So we can have, if a is 1, then of course we just have 1 to the x, which is a constant function. Now, this is our definition in here. This is what we're going to say, this is what we're going to go with here. Defining a to the x as e to the natural log of a times that x in the exponent. Defining it that way is actually lends itself well to the rest of what we've already worked with. By using that definition, it forces us in a way, or enables us to use this definition here for the log of x base a now, with a different, other than the natural log of x. So from now on, natural log of x, it really, you could think of it as a log with a base e, like that. Okay, log with a base e. But so this is just easier to write, but they mean the same thing. Okay. Now, okay, so this is our definition here for the log of x base a. It's really just natural log. It's a correction factor in front here. So it's basically the same function, but there's a factor here. It's a stretching factor in a sense. So it's very similar. Likewise, this function up here is very similar, but there's also a, in a sense, a stretching factor involved here. So you have that stretching factor. Here we have a few of the properties that result for these inverses. And this one here, of course, we'll use this extensively. These are not inverses. This is just an alternate way to write the two of them, one versus the other. Gives you a way to go back and forth. The second property is just, it's a result of the composition of two functions that are inverses of each other, a to the x and log of x base a. When you compose them with each other, you get that a. Likewise, number 3 is the same thing, but it's the other composition. So this would be true. Logarithm with a base 10 is called a common log. Okay, common log. And now let's solve a couple equations. This one here. It literally transforms itself using this form, the one that we have right here. I've circled number 1. If you have log a you have x equals log a y, then this becomes a to the x equals y. So what I have here, this would become 3 to the x equals 1 over 81, using that logic, okay, because of this property here. Now, this can be solved conveniently because we have 3 to the negative 4, which is equal to the 1 over 81. And because this exponential function with a base 3 is continuous and 1-to-1, we know that the answer to this x must be the negative 4. It's the only way you can have 3 to the x equal to 3 to the negative 4 is if the exponents are equal. So there's your solution. X is negative 4. Okay, let's get the next one. Here you've got a variable inside the log, so you're probably going to need an exponential to work with it. But before you do that, get these logs together. Okay, get the logs together as one expression. And I'm not going to convert them yet, although we could. Any property that It is applicable to the natural log. It's also applicable to these non-base E. So I can write this like so. Then I can do my conversion. 3 to the 1 equals x times x minus 2. Then I'm going to square or multiply this out and subtract the 3. So I get this. That gives me x is 3 and x is -1. Now, the -1 you can't use because we assumed over here that negatives were not usable. So can't use a negative for this equation. So the negative's out, but the 3 looks like it should work. You can do a quick check. Let's do this check here. Does that equal 1? Well, here, this is a 1. 3 to the first power is a 3. This one is log to 1. So that must be a 0. So up to that point, we weren't sure. Now we're sure. So we do have a solution. X equals 3 is our solution.